Hello, I'm George Chochia. I'm going to talk about matrix block all-to-all and all-to-all V algorithms designed by the Spectrum MPI team at IBM. So this work actually started as an attempt to improve performance of the BRAC algorithm. So we're focusing on short messages. And as a result of this effort, we're trying to reduce the number of stages by utilizing aggregation, message aggregation in the BRAC algorithm. But then it evolved that we removed actually a lot of the stages, that changed the complexity of communications altogether. So I'll talk about that later. Just all-to-all is an operation which can be represented as a transposition of the data. For instance, if we have a set of 4 processes, each of which has data dedicated to other processes, which is also called a personalized communication. And we can represent this as a matrix. The original matrix is shown on the left. And as a result of all-to-all communications, we actually perform a transposition of that matrix, and that's the operation that we are interested in. So if you look at the literature, you may find different papers which talk about different types of algorithms, for instance, linear, pairwise exchange, logarithmic, and we would call hardware-oriented. So these types of algorithms, they usually target different message sizes. For linear and pairwise exchange, it's traditionally large messages. For logarithmic, like BRAC or recursive doubling, it's they designed for small messages. And hardware-oriented algorithm, they could be designed for small and large messages. For instance, we can mention exploiting the core direct technology in InfiniBand to reduce jitter, or analyzing or optimizing network routing tables to reduce network contention. So the algorithm we are going to talk about, matrix block, performs best with short messages and large PPN. So you have to bear this in mind. Up to now, the libcall library in Spectrum MPI implemented BRAC and pairwise exchange algorithms. So these are 2 algorithms that we will be using to compare performance with matrix block all-to-all. So just to refresh you on what BRAC algorithm is doing, and I'll have this slide, and mention that BRAC algorithm actually works for different radiuses, and but most popular implementations are with radix 2. So here we have 4 processes, and again, on the left we have the original matrix, and at the end we should arrive at the transpose matrix. So what is essential for that algorithm is that it performs a series of rotations, and there are log base 2 R, where R is the number of processes, number of rotations which perform communicate imply communication between the nodes, and a fixed number of on the node rotations. And so the total number of rotations is logarithmic, and that actually allows to reduce the total number of messages to be sent. And this reduction comes at the price of that these messages have to be aggregated. So the aggregation, for instance, on step I, the rows that will be selected for rotation will be selected by the if a binary digit being not zero in the node number that is shown on the left. So we have, the enumeration of the messages to be sent on the left, and the non-zero value in a particular binary representation would indicate the row that will be selected for rotation. For instance, on the first step, it will be these rows, 2 rows. On the second step, there will be these 2 rows which have non-zero bits in the second digit. But messages itself at each step have to be aggregated. For instance, 0, 1 and 0, 3 here for process 0 have to be aggregated. And with all-to-all, the number of messages sent is all messages have the same size for each process, and they can be packed in a buffer of the fixed size, which is not the case with all-to-all V, and that introduces additional complexity for that algorithm. So now we have a very high view of the matrix block aggregation for all-to-all. And we have, again, 4 processes, but now assume that 2 of these processes are in node 0 and the other 2 are in node 1. So what we'll have to do is to, for processes in the same node, we have to just, we can represent this blocks as a matrix, and what we see that the transposition implies that processes that are on the same node, they just have to be transposed on that node, data belonging to these processes. And if we look at this data in these processes as a matrix, this is shown here. We can represent the operation as a transposition for data on the same node, and exchange between nodes for data that's not on the main diagonal. And in this case, we just have, once we have this data aggregated in the matrix, we have a direct communication between the nodes. We don't. We have only one stage in this case to exchange data. But again, like in the Brack algorithm, we have these messages aggregated. So this is just the basic idea of the algorithm, which repeats 3 steps. It packs a matrix block from input rates in shared memory, and it's exchanged. These blocks are exchanged between blocks between nodes to and from shared memory, with all the ranks on the node driving I/O to different nodes. This is important. So we can use, consider this each rank as a leader. So we have up to the number of leaders equal to number of processes per node, which is P in this case. And at the end, we need to unpack matrix blocks from shared memory to output array. Because we're using shared memory, it is important to look how big the shared memory space we need for that. And The minimum space of the algorithm is p squared times m, where m is the maximal supported message size. But for performance reasons, and in this case, we will only use a single process to send to exchange data. If we want to use all processes to exchange data with other nodes, then the amount of data is p cubed times m. For IBM Power 9 nodes, which are used on Summit with 42 processes per node, this translates to 1.1 gigabyte, assuming that the maximal message size is 8 kilobyte. We allow environment variable to use smaller message memory footprints, and they can be set between p squared times m to p cubed times m. The algorithm has been extended to support not only equal number of processes per node, but any number. So, and in this case, we're dealing. So the matrices are not become rectangular rather than square. But on the main diagonal, we always have square matrices. So on the main diagonal, we have matrices that will be dealt with on the node without communication with other nodes. It is important to evaluate performance, and to do so, we follow the Brack paper, which introduced a metric. This is a simple metric. It's not perfect, but it's I like it for its simplicity. So this metric is time, which is represented a completion time of the algorithm, which is consists of this C1 argument parameter, which is a message count per process. It's actually the maximum of message count per process. C2 parameter, which is a data volume sent by process. Beta is the latency of this is MPI latency, and 1/2 is the minimal bandwidth per process. So on the right here, we are showing a ping pong benchmark, and just to demonstrate that sending short messages, for instance, if you look at 8-byte messages, that is significantly more expensive than sending a large message with the same. So sending short message many times is significantly more expensive than sending a large message once. And for that reason, it is beneficial to aggregate short messages into a large message when possible. So the reason is simple, because there is an overhead for MPI, and the send incurs some overhead, and this overhead is significant. And typically when we send a large message, we're using RDMA, and RDMA has a one-time overhead for large message. So we'll use this metric to evaluate performance. So the table here compares complexity for two parameters, C1 and C2, as it appears in Brack's paper. So I mentioned that this algorithm is designed for different radiuses, and it could be R here, which is, I think this should be R. And typical implementations of Brack algorithm have radix 2. So what we're seeing here is that the matrix block algorithm doesn't have a logarithmic factor that appears for C2 that appears in Brack algorithm. So the pairwise exchange and linear algorithm also don't have this logarithmic factor, and this product B times R is in fact optimal, so that you can send less data than that in Alltoall. But with regards to C1 metric, we see that a big difference between, say, pairwise exchange and the matrix block, and that we are sending p squared times less messages than the linear algorithm, which is if p is, say, around 40, and modern systems have large number of cores per CPU, could be over 60. Then p squared is a very large number. And still, it's asymptotically less than what Brack has, but Brack has a lot of allows to aggregate a lot of messages. So on that chart, we're seeing performance measurements on Summit with the PPN 42, which compare Brack to matrix block in Spectrum MPI. And we're seeing two trends. The first is that as we increase message size, the matrix block algorithm performs better. And the second trend is that as we increase node count, it also performs better. And this is in agreement with the metric predictions that we can derive from the metric. So on the left chart, we're showing performance of different configurations and different message sizes. So from 8 nodes to 256 nodes with message sizes from 8 bytes to 8 kilobytes. And as we're seeing from the left chart, the performance gain is over 5 for 256 nodes. On the right chart, we're seeing comparison with Brack and pairwise exchange, which is implemented in Spectrum MPI. And because with large messages, eventually linear algorithm or pairwise exchange they become optimal. We're seeing a reduction in performance gain. It's still quite big, even at 8K, but the difference between say pairwise exchange and the matrix block aggregation algorithm is that it consumes more memory, and if you increase the maximal message size, then that requirement puts a limit on how much memory you want to dedicate to this collector. So Alltoall V is more interesting in the sense that it had this challenge, as we mentioned earlier. With Alltoall, we have buffers of fixed size. With Alltoall V, we have buffers of variable size, and we have to solve the challenge of repacking variable size buffers at each rotation with messages of variable size. So this problem has been solved, but it introduces additional complexity. The second challenge with Alltoall is suboptimal performance for a mix of short and long messages. The thing is that Brack algorithm is designed for short messages, and if you try to include large messages, that that doesn't help. That makes performance worse. And with our implementation, we addressed both challenges. The first was addressed because this matrix block Alltoall allows messages to go directly to destination, though there are no intermediate stages. So essentially, messages go in one hop. And we designed a method to do packing and dense packing and unpacking for this algorithm. So everything, once data is packed, it can be sent is just with one operation. To address the second challenge, we designed a split algorithm in two phases. So essentially, it's a hybrid algorithm. In the first phase, messages on the a short message threshold are sent using the matrix block algorithm, as similar to Alltoall. And the messages above the threshold are considered to have a zero length. The second phase handles messages at or above the threshold using conventional algorithm for large messages. This idea is applicable to the whole class of V-class of MPI collective algorithms, and we just applied it to Alltoall V. So on that chart, we're seeing performance gain, again measured on Summit with ppm 42 for Alltoall V. We don't have Brack implementation for Alltoall V. We only have pairwise exchange, and we're seeing a bigger gain. So for instance, for 8-byte, again, we're showing performance from 16 nodes to 256 nodes, and message sizes from 8 bytes to 4K. And for 8-byte messages, we're seeing performance gain around 34. So it's 34 times faster. And as expected, as we increase message size, performance gains reduces. So for 4K messages, it's still over 2x. But for the reasons of memory consumption, we don't extend it above that. So if you're interested to see the actual numbers that we're measuring, they are summarized in this table on the right. In this case, we have dual EDR links in Power 9 connected to InfiniBand. So it's EDR speed on each link. So some implementation details in Spectrum MPI. We need to allocate and deallocate this shared segment at the MPI communicator creation and deletion time. Well, actually, we have a slightly different implementation where this shared segment are located on demand. For instance, if application is not using Alltoall, it will not allocate extra memory. And in Spectrum area, we also have allow a mix of algorithms to work together. We have so-called XML tables, which parameterize the task count per node and node count, and the algorithm is selected based on the table which performs best for this set of parameters. So memory-sensitive applications have a choice to tune the shared memory segment size, bearing performance trade-off in mind. So the smaller shared segments would have some performance impact. It's not that dramatic, but it could be noticed. Or avoid this algorithm altogether if they're very sensitive to memory consumption. I think that's all I have. Thank you.
So I can try to repeat the question. So is the implementation only working at two levels of hierarchy, intranode and internode, or can that be parameterized as well?
I would say that there are there's basically two different or independent operations in the algorithm. One is internode and the other is extranode. So there is no dependency between them. So the first we start with the internode and then follow by internode communication.
I have another question. Have you also looked at the distribution of message sizes for MPI, like the all-to-all V? Like, what kind of distributions have you looked at? Like, message size can be like they can follow like power law distribution or Gaussian distribution. I'm just curious on that one.
No, we didn't investigate what is the typical distribution per application, right? I mean, it's interesting, and I looked at some point how often MPI Alltoall V is used in general, and I was surprised that it's actually widely used. I mean, I don't know how reliable that source was, but there are many applications that are using Alltoall V, and but the actual distribution of messages is no, I don't have the answer to that, but I would think that there is not a big difference between message sizes. That's what I would expect. So I don't think that there are usages when there is a huge message and then there are a bunch of short ones. But what is the like standard deviation or around the average? I don't know.
Okay. Thank you. Just one another follow-up question. Like, how sensitive is your implementation with respect to number of cores per node? Like, do you like? Is there a variation in performance you see with varying number of cores per node?
Yes, certainly. I think I missed one important point. There is actually a formula that is shown in this presentation. It's in the paper as well, which indicates the scope where Braque algorithm is optimal or performs better than our algorithm, and that formula has a parameter of processes per node. So it is not an exact representation of what you would measure, but it's a ballpark, the ballpark. And it shows that the more processes per node you have, the bigger advantage you get, the bigger is the gain. But if you reduce the number of processes per node, it will perform just like a typical linear algorithm because there would be nothing to aggregate. For instance, if you have one task per node, then there is nothing to aggregate. So suddenly it will show no advantage.
Any other question? All right. Let's thank George for this excellent work.